All right, welcome back. Last time we talked about quite a bit. So we talked about the Čech derived spectral sequence. We talked about the Meyer-Vietoris long exact sequence, which lets you compute the Étale cohomology of a scheme if you know the Étale cohomology of a Zariski open cover. We talked about Étale cohomology of quasi-coherent sheaves and how that just agrees with Zariski cohomology. So that was our first legitimate computation actually in Étale cohomology. Like we now know the cohomology of a lot of sheaves on the Étale site. And then we used that to compute the Étale cohomology of FP. And I wanted to, because Robert asked about that right before we started recording, I wanted to make a couple remarks about that. So let me recall what we did at the very end of last time. And that'll be a good lead into what we discussed this time. So last time we have a scheme X over FP, and we observed that there's a Arden-Schreier exact sequence. So this is an exact sequence of sheaves on X Étale, the small Étale site, which starts with the constant sheaf FP and goes to OX, and then again to OX. And this map here it sent t to the p minus t, where t is a function. Okay, and you should check that this is actually an additive homomorphism. It's a homomorphism of abelian sheaves, and that's because Frobenius itself is a homomorphism. So maybe it's worth noting. I mean, here I assumed X was over FP. This works over an arbitrary base of characteristic P. You just have to think a little bit more carefully about what you mean by t to the p, and what you have to do is you have to work with relative Frobenius. And I won't get into that until maybe later in the course, where we are really getting into Frobenii. But what you should take away from this is that there is a similar story over any base of characteristic P. Okay, so what this gave us was a long exact sequence. So this gave us a long exact sequence which goes from hi minus 1 of x ox Étale. Well, that's just the same as hi minus 1 of xox, like the usual Zariski cohomology by the theorem we proved last time, that Étale cohomology of quasi-coherent sheaves agrees with Zariski cohomology of quasi-coherent sheaves. Then this maps to hi of x Étale with that FP coefficients. This maps again to hi xox, and this maps to hi xox, again by this Arden-Schreier map, x to the p minus x, and then so on. Okay, so I think what Robert asked about is, okay, what's the answer? Like, how do we compute hi of FP? And in general, that's not something we exactly know how to do. But what we can say is that in the affine case, it's very, very easy to understand. So if x is affine, then hi of xox, or with the same with any quasi-coherent sheaf, is 0 for I bigger than 0. So what we get is we just get an exact sequence 0 to h0 xfp. That's just fp to the number of connected components of x. So that's fp to the pi 0 of x, if you'd like. That maps to ox of x. So just global functions on x. That maps to ox of x. This map is this Arden-Schreier map, t to the p minus t. And then the co-kernel of this map is h1 xfp. When I write h1 xfp, I now mean in x Étale. I'm going to omit that. Okay. So this is the answer in the affine setting, and what I wanted to remark is that this is in general not finitely generated. So for example, if you take x to just be the affine line, you're getting the co-kernel of the map sending t to the p minus t as a map from k adjoint t to k adjoint t. You should check that that's not finite dimensional in general. It's an FP as a vector space. For example, this is actually quite easy to see if you work over a much bigger field. I mean, then already when you take the ground ring, the k goes to k via the map t to the p minus t. That's going to have huge co-kernel in general. So this tells us that in characteristic P, Étale cohomology with FP coefficients is poorly behaved, in the sense that, well, usually you expect if you have a nice cohomology theory, it should assign to every scheme a bunch of finite dimensional vector spaces. And here, at least for affine schemes, it's not doing that. So the remark I wanted to make is that if X is proper, then HI X Étale with coefficients in FP is finite dimensional. Can anyone tell me why this is true? Arvind asks, by the way, in chat, is OX Étale different from GA? No, it's the same. So GA is the representing object for OX. Yeah, that's a good question. Yeah, sorry that I switched notations. Yeah, so can anyone tell me why this remark is true? Well, so I claim it follows from this exact sequence.
Because HI of OX is finite dimensional.
Yeah, exactly. So by proper push forward, by coherence of proper push forward, what we've done is we've sandwiched these terms we're interested in between some finite dimensional things. So they better be finite dimensional. So this is by proper push forward for coherent cohomology. Right, so we've deduced this the finite dimensionality of these Étale cohomology groups from some finite dimensionality of coherent cohomology groups. And actually, I mean, this is kind of this even though I'm telling you that H1 of FP or HI of FP in general is poorly behaved, and indeed, even in this proper setting, like these groups won't have the dimension you might expect. For example, so just as an example, for E an elliptic curve over an algebraically closed field of characteristic P, it's not so hard to see from this long exact sequence that H1 of E with FP coefficients is going to be one-dimensional, so it'll be FP, if E is ordinary, and 0 if E is supersingular. And this just follows again from this long exact sequence, and one definition of supersingularity is in terms of how Frobenius acts on these groups. Cool. So what I want to say is like this dimension is probably not what you would expect. Like if you were taking the cohomology of an elliptic curve in characteristic 0, you would expect it to be H1 to be two-dimensional, right? It's a torus. So here we get something which is 1 or 0-dimensional. But nonetheless, these groups with this Étale cohomology groups with FP coefficients, like I think often when you take a first course in Étale cohomology, you think of these as horribly like pathological things, but like I want to just stress, like I think they're actually interesting and useful. Like it's not, they don't form a good cohomology theory in the sense like they're not going to prove the Weil conjectures, but they're still shadowing very interesting information. So this data is still closely related to like crystalline cohomology or other kind of p-adic cohomology theories. And it's useful to think about. And I don't want you to think of this as like the scariest thing in the world. It's just an interesting thing, which is not a good cohomology theory in the sense that it doesn't behave like a cohomology theory in characteristic 0. All right, are there any questions about that? All right, so that's the sort of business from last time that I wanted to finish. Okay, so I want to give another example. So this is an example we can kind of make explicit now using Czech cohomology. So I want to talk about the cohomology of the Étale site of a field with coefficients in some sheaf F. So we're going to compute this using Čech cohomology, and I want to compare that to what we know, what we already said. So can anyone remind me how we already tried to understand this? We actually already worked out what this is. So can anyone remind me like how do you characterize sheaves on the Étale side of a field?
By using Galois descent on.
Yeah, exactly right. So what we said is that sheaves on spec K Étale, so let's say abelian sheaves on spec K Étale, were the same as discrete G modules, where here G is the absolute Galois group. Okay. Okay, and I'll just verbally remind you what the functors go both ways are. So given a sheaf, you want to try to evaluate it on the separable closure of K. That doesn't quite make sense because that's not an object of the Étale site. It's not locally finitely presented. But what you can do is choose a separable closure, look at all intermediate extensions between K and its separable closure, and take the direct limit of what you get by evaluating the sheaf on those extensions. Alternatively, given a discrete G module, you can say what its value is on a finite extension of K by taking its Galois, the fixed points of the absolute Galois group of that finite extension. Okay, so that's the bijection, and one of your exercises was to check using Galois descent or Étale descent that's an equivalence of categories. Okay, and then what we said was the corollary of this equivalence of categories was that Galois cohomology, or sorry, it's that Étale cohomology and maybe let me call this equivalence, I'll call it iota. We said that this was canonically isomorphic to Galois cohomology. Right, and that's just because derived functor cohomology only depends on the ambient category and the functor out of it. And here we've said these two categories are the same, and we're taking the derived functor of global sections on the left and G invariants on the right, and those are kind of the same functor under this identification. Okay, but now we can actually make this explicit. So we can use Čech cohomology to make this explicit. So can anyone tell me how to do that? Does anyone see? So let's actually write out the Čech complex for a sheaf F. So what do we need? So let's compare to Čech cohomology. And by Čech cohomology, to start with, let's just say we have a cover of spec K. Okay, so can anyone give me an example of a cover of spec K?
A separable extension.
Exactly right. So let's set U to be spec L, where here L over K is a separable field extension. So what does the Čech complex look like? So this Čech complex is just f of U, so f of spec L, to f of U cross U, so on and so forth. And now let's assume, and let's assume that U is Galois. So let's assume L over K is Galois with group, let's say G L over K. So can anyone help me rewrite this complex? So what is U cross U if L is Galois over K?
L to the degree, I guess. Spec L to the degree.
Yeah, and another way of saying that is it's just the Galois group times spec L, right? So then this complex actually just becomes f of U to f of the Galois group times u, and then we get f of the Galois group squared times u, and so on and so forth. Okay, and then the claim that you should check is that this complex is the same as the standard complex, meaning inhomogeneous cochains, which computes Galois cohomology. So computing hi g of L over k with coefficients in f of u. Okay, and this is an exercise. At least from what we've written above, it should be not so hard to see that the terms are all the same. And then what you have to do is identify the differentials. So if you haven't seen Galois cohomology before, that's fine. You should think of this as the definition. Okay, and then from this, it's immediate. The following corollary is immediate, that this sort of direct limit check complex so this is what you get just by taking the direct limit of all the of these CU over spec Ks for all U is quasi-isomorphic to the usual complex computing Galois cohomology. And why is that? Well, it's because that complex is just the direct limit, is precisely the direct limit of these things. And that's the definition. Okay, so what I want to convince you here is that, you know, even if that Czech cohomology stuff seemed unfamiliar, if you've seen Galois cohomology, you've done Czech cohomology before. All right. Are there any questions about that?
I was actually wondering, I don't, it may be a little afield, but are there any nice spaces where like the Galois cohomology and the Étale cohomology coincide, or?
Well, I mean, spec K is an example, but maybe...
I don't know. Sorry, I'm eating oatmeal right now. I didn't notice.
That's okay.
Yeah.
Yeah. So that's somehow does that answer your question, Amelia?
Yeah, it does. Yes, it does.
Okay. Yeah.
I was guessing. I guess more importantly, though, is there like a sort of general characterization of these spaces? Or?
Yeah. So the answer is kind of yes. So okay. So when you say Galois cohomology, maybe let me reinterpret that, and let me. So Amelia asked the following question, and I'm going to reinterpret it as follows. So Galois cohomology is an example of group cohomology. It's you have a group. It is acting. It has some kind of action on a module, and then you're taking the derived functor of the invariance. So you can ask, when can you compute Étale cohomology as some kind of group cohomology? Okay, and you could similarly ask this about singular cohomology or your other favorite cohomology theory. It's a totally reasonable question. And the answer, and this is in some sense a fake answer, but in some sense not a fake answer, is that the answer is this is true if your space, so the space whose cohomology you're computing, is a k-pi1 space.
Is that like a God? What are those things called?
Yeah, I'll say what I mean by it. So in topology, what this means is that it's connected, and all of its homotopy groups vanish above degree 1. So it's in other words, it's the classifying space for a discrete group. So as an example, the circle S1 is a space where pi1 is Z, and all the higher homotopy groups vanish, and so that's a KZ1. Okay, and there are lots of other examples. So for example, if you take a compact orientable surface, its universal cover is contractible as long as its genus is at least 1. And that tells you that it's a k-pi1 for its fundamental group. Okay, and if this is the case, so in topology, then singular cohomology of such a space is the same as group cohomology of the fundamental group of that space. Okay, so why do I say this is a fake answer? Well, it's a fake answer because this is more or less the definition of a k-pi1 space in algebraic geometry, namely that its cohomology is computed in terms of the group cohomology of its pi1.
Yeah.
And I haven't yet told you what pi1 is in Étale. I will later in the course. Oh, sorry, Ali, go ahead.
Will BG be an example of this, like with stacks and stuff?
So BG for G a finite group will be, yeah. For G, like for GLN, it will not be. Yeah.
But yes, that does help. I may bug you after class a little.
That sounds great. Yeah, you're welcome to do so. Yeah, so this is a really interesting thing, and we actually talked a little bit about this last time, maybe implicitly. So when we talked about Arden neighborhoods, those are going to be examples later of Étale K pi ones. Great. Any other questions about this?
When you said Arden neighborhood, was that the example of how we showed that the Arden Schreier thing was surjective?
No, sorry, that was something else. So it was, maybe this only came up in office hours, if I remember. So there was, but so we discussed how you could cover a space by opens, which you could write as kind of special fibrations where all the fibers were curves, and over some lower dimensional base with some extra properties.
Sorry, thanks.
Yeah. So that's sorry, I forgot it was actually only in office hours. So if you were in office hours, you heard a little bit about Arden neighborhoods, which are examples of K pi 1 spaces. But we'll see later, for example, that if you take an affine curve, that will be an example of a K pi 1 space in Étale cohomology. Are there any other questions? Okay, well, if not, then we're going to move on. So the goal for the next few class periods will be to try to compute the Étale cohomology of some actual spaces. So maybe let me actually write that out. So the goal for the next few classes will be, sorry, maybe the colon should go after that, will be to compute the Étale cohomology of curves. Of curves over a field K equals K bar. And what I mean by this is the HI of C Étale, Z mod L to the n Z. So this is what we want to compute. So C will be a curve, meaning a smooth, maybe not necessarily projective curve over a algebraically closed field. And we'll want to compute its Étale cohomology with Z mod L to the n Z coefficients, where here L is not equal to the characteristic of K. And in fact, we more or less already computed it when L equals the characteristic. So this is the interesting case that's left. And the claim is that it's going to look a lot like what you think it should be if you know what the singular cohomology of a Riemann surface is. So in particular, at least the dimensions of the cohomology groups will be the same. And in fact, the hard part will be computing this for I bigger than 2, where you would expect these groups to be 0, because you think maybe a surface, a Riemann surface, is 2-dimensional, and indeed they are 0. But that's going to be what we're going to spend most of the time on. But today, I want to get us to the point. So today, we're going to try to get to the point where we do this for I equals 0 and 1. Okay, and in order to do that, I need to give you a, well, 0 is easy, actually. So here, HI C Étale, sorry, H0, Z mod L to the NZ. So can anyone tell me what this is? Maybe let's suppose C is connected.
Z mod L and to Z.
Yeah, so we're just asking what the global sections of this sheaf are on a connected space. And well, the definition of this sheaf was just maps into Z mod L to the NZ. That's disconnected. So a map from a connected, it's a disjoint union of points. So a map from a connected space in is just constant. So it hits one of those points. Okay, so we've computed H0. So now we're going to try to do H1. Okay, and in order to do H1, I need to give you a kind of interpretation of H1 X Étale F. And that interpretation will be in terms of objects called torsors. In terms of torsors. Okay, so let me make a definition. And this is the definition of a torsor. Let me call it a Gtorcer, where here G is a sheaf of groups, not necessarily abelian, on X. And this will actually make the definition will make sense for any site, but let me just make it in the Étale site. Are there any questions, by the way, before I say what this definition is? So the goal is today we're going to try to figure out what H1 of a curve is, or actually we'll basically do H1 of any variety.
I just wanted to clarify what your definition of a curve is. Is it complete? Is it smooth? Is it?
Sorry. Yeah. So well, I think so far, not that everything I've said is true for any, in fact, any connected scheme. But yeah, so what we're actually going to compute is we're going to compute the cohomology of smooth connected curves, so smooth separated schemes of finite type and of dimension 1 over an algebraically closed field.
Thank you.
Yeah, I guess I said smooth, so that smooth implies finite type. Yeah, but that said, like going from that to doing so we won't assume properness, although the interesting computation will be the proper case, you know, going from that to doing more general curves. So for example, singular curves will not be so hard, and I mean probably we'll do that later in the curve. And Jose asks in chat is if H0 is just the group to the power of the number of connected components, and that's correct. Yeah. Yeah. So again, I'm just from Bijection, for example, it's not so hard to do disconnected curves once we do, or disconnected varieties once we do connected varieties. And we've already talked about Bijection. Are there any other questions before I start talking about Gtorsers? All right, so what is a Gtorcer? Well, it's going to be, the definition will look a little bit scary, but we're going to talk about a lot of examples. But what this is supposed to be formalizing is the notion of a principal homogeneous space. So for example, if you have the sort of typical example of this is if you have a Galois covering space, so you have a space X and a Galois cover of it, just in ordinary topology, maybe it's a manifold, then that will be a torsor for the Galois group. And what that means is the Galois group acts on the space and it acts simply transitively on every fiber. So the idea here will be a sheaf F on X Étale, so a sheaf now of sets on X Étale with an action by G such that G acts simply transitively on every fiber. Okay, so this is just the idea. You could, if you wanted to, turn it into a definition, but instead I will give you the standard definition. So the actual definition is the following, and then I'll try to compare these. So you're supposed to think this top thing is like what it means to be a principal homogeneous space. So the actual definition is that a torsor is a sheaf T in sheaves of sets on X with an action. So far we're just doing the same as the idea definition, G times T to T. So do you guys want me to write out what an action is? So a group action is a bunch of, like, you need that if you act by G on H times T, that's the same as acting as via G times H times T. Sorry, is G times H times T. It's like, so there's some commutative diagrams that have to be satisfied. Another way of saying it is just that, like, when you evaluate this natural transformation on any object of X Étale, it gives you an honest action of G of U on T of U. But maybe I won't write out the diagram unless someone requests it. Okay, I'm getting some thumbs up. So it's an action like this, which just means, for example, when you plug in an object of X Étale, you get an honest action. And then the following condition has to be satisfied. So this is how we make sense of acting simply transitively. So it's such that the following map is an isomorphism. So there's a map from G times T to T times T given by A, comma, the projection onto the second factor. And the requirement is that this is an isomorphism. Cool. My lights are flickering, so I'm a little worried that I'm going to lose power. Is anyone? Am I still audible to you guys?
Yep, still good.
Okay, cool. So we'll see what happens. Exciting times. All right. Okay. So cool. So maybe it's worth remarking. So this is kind of a funny point of view. But what does this condition say? So it says that T times T, I'm reversing the arrow here, is isomorphic to G times T. And one way of writing that is that if you pull back, so by the way, these fiber products are over X, and they're products in the category of sheaves. So one way of saying this is that if you pull back to T, then so that's T times T, then you get a trivial torsor. Which means just the following example. So what is a trivial torsor? It's the following example of a torsor. So G is a G torsor, just via its action on itself by left multiplication. Okay, and that's what it means to be the trivial torsor. So what is a G torsor? Another way of saying this is it's a sheaf of sets with an action by a sheaf of groups, so that when you take its fiber product with itself, that action just becomes the action of the group on itself. Okay. Are there any questions about that? So this is that was kind of a mouthful. But this is a really cool general principle, and it's actually very closely related to this trick that showed up in the proof of FPPF descent, where we base changed to a cover to check something. And here we're doing the exact same thing. We're base changing the torsor to trivialize the torsor.
So you see pull back to T, but T is a sheaf, right?
That's true. So nonetheless, multiplying by something is the same as taking the pullback. So if you'd like, you can think of this as the fiber product over the terminal object of sheaves on X. But what is that? It's X. It's the functor represented by X. So you should think of this fiber product as a pullback, actually. Does that make sense, Arvind? And that's literally true if T is represented by an X scheme.
Is there no representability criterion like that?
We'll get one in a minute. Yeah, we'll get one in a minute. Yeah, so that's a good question. Yeah. Okay. So maybe I want to give some examples maybe before talking about representability. So here's an example. So suppose G is just a finite group. And then underline G and sheaves on X Étale is the corresponding constant sheaf. So that's just maps into the scheme G, right? That's why it's a sheaf. Then can anyone tell me what is a G torsor? Or can anyone give me an example of a Gtorcer?
Take a cover with Galois group G.
Yeah, exactly. It's a finite Étale cover. And in fact, there's an equivalence of categories, which we'll see in a second with Galois group G. So if you'd like, you can think of that, let's say if X is a smooth curve, you can just think of that as a Galois extension of the function field with Galois group G, which is unramified everywhere. All right, what about a, so let's let GM, so here's another example. So GM it's well, as a sheaf, it sends U to units in the functions on U.
Something happened to your screen sharing?
Oh, sorry about that. Let me try to fix that. Uh-oh. I think I got it. Do you see it? Oops.
Yes. Nope.
What is going on?
A very pleasant background, by the way.
Okay, do you see it now? I think you guys know my code now. Do you see it now?
Yes.
Okay, great. Sorry about that. All right, so everyone on YouTube is going to know my iPad passcode right now. Oh well. Something to remember to change. All right, so this is the sheaf that sends Étale X scheme U to the sheaf of invertible functions on U, and let me just remind you, so GM is represented by maps into spec, let's say wherever field K, T, spec KT, T inverse. All right, are there any questions about this? So I think we've talked about this in the past. All right, let's do it. So Sarah is telling me I did expose my Wi-Fi name, but not my passcode. Okay, so can anyone tell me? So can anyone give me an example of a Gtorcer, of a GM torser?
Line bundles.
So is the line bundle literally a GM torser?
Minus the zero section?
Yeah, exactly. So if you have a line bundle, so if you have a physical line bundle, so an example of a GM torser is a line bundle minus the zero section. Okay, and let me be explicit about that. So let's actually make the GM torser. So to L, we're going to take the following. We're going to take the relative spec over X of the direct sum of L to the tensor N, where here N is in Z. Okay, so if you look at fibers of this over X, you can see, so Amelia missed the Wi-Fi name, so if someone saw it, you should feel free to share it with her in chat.
They did.
So if you look at fibers over a point in X, what is this? It's just K adjoint TT inverse. So the fibers of this look like GM. Okay, and how does GM act on this? Well, T acts on L to the tensor N via T to the N. So that's the action. So this is the functor this represents, if you'd like, is a GM torser. Okay, and in fact, we'll see in a little bit. So we'll see in a little bit that this is an equivalence of categories, or sorry, not equivalence of categories. So there's a natural bijection between GM torsers and line bundles. If it's an equivalence of categories if you only allow isomorphisms between line bundles as morphisms in your category. Okay.
Sorry,
Here's an
and
example.
0 here is just OX, right?
I'm sorry?
L to the 0 here is just OX, right?
That's right. That's right. So this is tensor products over OX, which means that if you take the 0th tensor power, that's just OX. Great. So what if G is GLN? So can anyone describe GLN torsors for me?
Like this is going to come from like vector bundles again.
Yeah. So the claim is that which I'll talk about in a little bit, is that there's a natural bijection between GLN torsors and vector bundles of rank n. So can anyone tell me, like in words, what is that bijection?
But looking at the co-cycle data?
Yeah, so you can look at co-cycle data, that's right, but that will use something that we don't quite have yet, right? So that'll
okay.
that GLN torsors are locally trivial, which is not so obvious. So there's another description. Does anyone know it? So what it is so to E, you associate the bundle of frames is what it's called. And so what this is the fiber over point is the set of bases for the fiber of E over that point. Okay. And this is something I told you what it is on fibers, but in fact, if you just slightly change that, you would get what the functor rate represents is. And in fact, Ben in chat told us the answer. It's just E goes to isom. So the isom sheaf over Étale with O to the direct sum n E. So what that means is its value on some cover U is the set of isomorphisms between the trivial vector bundle and E over U. So that's what it is as a sheaf. Okay, and it's not totally obvious from this description that this is actually a sheaf. Okay, and then the claim is that this is a natural bijection. Are there any questions about that? So this, at least, I think, gives you pretty clearly a functor from vector bundles and isomorphisms to GLN torsors. Yeah, that's well said. That's a good way of thinking about it. And maybe it's worth noting. I mean, so what is an isomorphism? Like, how does this compare to what my description of the bundle of frames from before? Like, what is an isomorphism between O direct sum n and E? It's like a basis of E, right? It's a basis of every fiber, in fact. Are there any questions about that?
What is the inverse to this?
Yeah, that's a good question. So suppose you're given a GLN torsor. So suppose you're given some T. So here, this is, maybe let me make a table here. So this is vector bundles here, and this is torsors. So how do you go from a torsor T to a vector bundle? Well, one way of saying it is you take T times OX to the n, and then you quotient out by GLN. So the point is this quotient kills T, and so each fiber will be isomorphic to the fiber of OX to the n, because you're supposed to think GLN is acting simply transitively on T. But it will twist up the OX to the n by the way that T is twisted up. So that's maybe some slogan for what's happening here. And what do I mean by this quotient? By the way, I mean the quotient in the category of Étale sheaves. So okay, so there's some content here, which is to check that this is a vector bundle, and that's not obvious. That actually really uses something. In particular, it uses that GLN is smooth.
And can you specify the GLN action on T cross OX?
So this is the diagonal action. So T is a torsor, so GLN acts on T, and GLN acts on OX to the n, because if you have a matrix, it acts on n by n. It acts on OX to the n. Right. Does that? GLN is literal. So what is GLN? The definition
just
of
a
it
natural action in both
is
components.
ought of OX to the n. Yeah, so the action is the diagonal action. And so here, this action is the diagonal action. Does that answer your question, Arvind?
Yeah, I guess I'm asking this because I've seen this different action where you do an inverse on one side and just like the usual.
I think because I wrote the GLN on the right, I actually should do that. Like I should do an inverse because the way I wrote actions was GLN acting on the left. But if you could also just put the GLN on the right, and then you wouldn't have to worry about that. Yeah, so it's what you need to write down to make it a right action.
Okay.
Yeah, but you could also just as well put the GLN on the other side, and then you would just get the diagonal action. Yeah. Are there any other questions about that? All right, let's take maybe a 2-minute break since we're about halfway through. And then we'll continue talking about torsors. So far I haven't explained how these are related to H1, but just a reminder, the goal is to get some kind of concrete description of H1s. So how are you all feeling? So Ben Church, can you play the same game and take the associated vector bundle -0? So I mean, you can do that. That's a thing. It's not a GLN torsor. And the reason why is, well, what are the fibers? The fibers are just vector spaces -0. And unless the rank of that vector space is 1, that's not isomorphic to GLN. Does that answer your question, Ben? Yeah, I mean, in fact, they're even the wrong dimension, right? If GL2 is 4-dimensional, but a 2-dimensional vector space -0 is 2-dimensional. Yeah, so there's some funny coincidence that that GM is somehow is 1-dimensional, and so is GA, and the general statement GLN and GA to the n, those are quite different looking objects. Yeah. Any other questions for the break? Maybe let's wait 1 more minute before reconvening. Cool. All right. So let's. I see. Is there a scheme representing the frame bundle like how spec O plus L to the n does for L? Yeah, you could. Yeah. So Ben wants to know, like, can you concretely write down this isom? So this this isom scheme over here, or isom sheaf, and the answer is yes, but it's a little complicated. So the way I would do it is I would write it down locally. So locally a vector bundle is trivial. And then you're writing down just GLN, and I think you probably know how to write down that's spec of the polynomial ring and n-squared variables with the determinant inverted, and then you would glue. So we'll talk about gluing in a section. In a section. We'll talk about gluing in a second. I'm getting ahead of myself. All right. So let's get back to it. So before I begin, any questions? Okay, so first I need to make a definition. So we say a Gtorsor T is split by a cover U to X if T restricted to U, or the Étale side of U, if you'd like, is isomorphic to G restricted to U. And this is as a torsor, not as a bare sheaf. All right. Are there any questions about what this definition means? Okay, so here's the remark. And this calls back to this weird thing I remarked earlier, that when you base change a torsor to its, yeah, so Ben says, is this locally trivial? And yeah, so this means, so if you're split by some clever, that means you're locally trivial. So the remark is that, and this is just from before, is that, so suppose T is representable, and that means that n T to X is a cover. And this now makes sense in any site. I mean, I've been defining things in the FPPF site, or sorry, in the Étale site, but everything I've written makes complete sense if you just replace all those Étales with FPPFs. Then T is split by T. Okay, and that just follows from this remark from earlier, that if you base change T to itself, you get the trivial torsor. So here's an example. So suppose G is a Étale group scheme. Over X. And T is a, sorry, let me say a finite Étale group scheme, just to be safe. And T is a Gtorcer, which is locally trivial, which is split by some U. Then I claim, first of all, that T is representable. And second of all, that, that T is split by T. Can anyone explain why this is the case? Any thoughts? So let's actually prove this. So first of all, I claim 1 implies 2. Can anyone explain why? Yeah, so Ben writes in chat, well, T times itself is trivial. That was exactly this remark up here, this remark. So in order to verify 2, all we need to do is verify that T is actually a cover of X if it's representable. So can anyone tell me why is T a cover?
Because after you base change to U, it's a finite Étale.
Exactly right. So when you base change to U, so T times U over X to U is a cover because it's finite Étale. It's just isomorphic to G times U. That's what it means to be trivial. Okay, and that means yeah. So you can check that something is a cover after base change. This follows. You should check that this follows from the axioms of after base change along cover. Sorry. So you should check that this follows from the axioms of a site. And that imply and then this plus the remark above means we're done. Okay, so now we just need to prove 1. So we need to prove T is representable. So the observation is that T is locally representable. So T times U So or maybe let me write it this way. So the restriction of T to the Étale set of U is representable. So why is that? Well, it's just because it's the same, because it's isomorphic to G restricted to the Étale set of U. And G was a finite Étale group scheme, and hence a scheme. Great. So that's step one. So how do we go from something representable on U to something representable on X? Yeah, sorry, Sarah, I missed your question. The claim is not that 1 and 2 are equivalent, it's just that 1 and 2 are true. So I first proved that 1 implies 2, and then it suffices to prove 1 to show that both 1 and 2 are true. Yeah, so can anyone tell me? So I have a representable functor on U, and I would like to do something to it to get a representable functor on X. What do I do?
Descent, right?
I'm sorry, my internet went out for a second. Could you repeat the last thing?
Yeah, sure. So what I said is that we're trying to show that T is representable. We observed that its base change to U is representable. And then we want to conclude that it's representable. And Arvin says, yeah, we should use descent. So what we need to use is we need to use, so we need to use effectivity of descent. Okay, and here's the scary thing. Descent is not effective for schemes. So what are we using about G to get descent, to get a descent? So in general, we discussed this when we talked about FPPF descent. You cannot descend a scheme. Even if you have descent data, you can't descend it necessarily. But sometimes you can. Can anyone remind me when? And my hint is that is this word finite here. Okay, what we're using is effectivity of descent for affine schemes. So finite things are affine. So in particular, yeah. So that's what we're using here. Other questions about that?
You mean it's affine over X?
Yeah, that's right, affine over X. And let me just remind you what we did is, well, we proved that descent was effective for quasi-coherent sheaves. But what is an affine scheme? It's like spec of an affine X scheme. It's like spec of a quasi-coherent sheaf of algebras. So all we have to do is descend that quasi-coherent sheaf of algebras. Yeah. Great. Okay, so we proved this. So what this says is that if we have so let me say this example, or this what is now a proposition in words. If we have a torsor for a finite Étale group scheme, it's represented by an honest G cover, right? It's not just a sheaf. It's actually a covering space. Okay, cool. Okay, so now here's the proposition. So I promised you we would give a concrete interpretation of H1. So can I repeat my remark about T cross U to U being a cover? Oh yeah, sure. So here the hypothesis was that G was split by some U. And what that means is that, well, what it means to be split is that when you pull back to U, you just get G over U. And G is finite, and finite Étale. So in particular, it's a cover of U. Does that help, Ben? So finite implies finite Étale. Well, Étale implies open, finite implies proper, implies closed, which is why it's surjective. Does that answer your question, Ben? Sorry, the map from T, the base change of T to U to U. And here, what am I using for Étaleness? I'm saying that G itself was an Étale X scheme. So when you base change to U, you get an Étale U scheme. Great. Yeah. So I should say, I mean, like when I do this stuff, I'm playing like fast and loose with the Untitled dilemma. Like I'm constantly shifting back and forth between a sheaf and a representing object. So if that bothers you, or if you're confused about something I say when I do that, you should ask me a question. I mean, that's something that is it's now so ingrained in me after doing this for a few years that I may not even notice when I'm doing it. Okay, so here's the proposition. So here's the promised concrete interpretation of H1. So I claim there's a bijection, and we'll see. We sort of already saw this in part 2 here, but we'll make it more explicit, which is that if T, there's a bijection between the set of T, which is a Gtorcer split by some cover U to X, and actually, does anyone have a guess as to what this is in bijection with?
H1 with G coefficients. Yeah.
So here there's a U here, right? So it better reference U, but you're right. So it's the Czech H1 U over X with coefficients in G. And maybe it's worth remarking, so I only define Czech cohomology with coefficients in an abelian sheaf, but this makes sense for G, just any sheaf of groups. Okay, and what do I mean by that? I mean, if you look at the formula for the differential in Czech cohomology, like if you only go up to degree 1, it still makes sense. It's still you don't have to make any choices.
Can I just ask a quick question?
Yeah, of course.
Here the U to X is one like surjective finite Étale cover.
It is a covering family, but I'm always if you assume some quasi-compactness, you can always replace a covering family with a disjoint union of the objects in that covering family. But yeah, this makes sense for any covering family.
I see. Okay, thanks.
Yeah. Okay. So can anyone tell me what the proof of this is? So I'm not going to give the details, but maybe can anyone tell me the map? So Ben says, is a sheaf of groups the same as a group object in sheaves? Yeah. So a sheaf of groups is the same as a sheaf of sets, which is a group object in the sheaf of sets, in the category of sheaves of sets. That's right, Ben. I don't think that's a dumb question at all. Yeah. Cool. So can anyone give me the idea of the proof of this?
Are we going to use the isomorphism we got from T to G when we go over U to construct like a cocycle?
Yeah, that's right. So what we get is so we get that T restricted to U. Let me write even Étale is isomorphic as a torsor to G restricted to U Étale. And this isomorphism is as a torsor. Okay, so what that means is that when we restrict T to U cross U in the two different ways, so maybe let me write it this way. So if we take, so let's write U cross U over X to U. So there's these two projections, pi1 and pi2. So once we do this, we get is an isomorphism pi1 star of T to pi2 star of T. Just this isomorphism just comes from the fact that we're pulling back something from X, right? So here we have a map to X. But we can view this via the isomorphism above as an isomorphism between pi1 star of G and pi2 star of G. Here we're just pulling back the isomorphism from before. Let me call this phi or something. So this is pi1 star of phi here, and this is pi2 star of phi. So what that tells us is that this descent data, which we have automatically because we were pulling back something from X, we can view as an isomorphism of trivial torsors, right? And here, what is this thing? This is an element of G, or a section. This is a section. This thing is in gamma of U cross U over X with coefficients in G. Okay, and this is something you have to check, that an automorphism of a trivial G torsor is just the same as an element of G. And hopefully that's very plausible. If you think about the case of a Gtorcer over a point, I think you'll see this clear. Okay, and what is this thing? The claim. So that the claim is that this thing. So this is what we call C2 of U over X G, right? That's just the definition. Or sorry, C1, I think. Yeah, C1. So the claim is that the cocycle condition implies that this is in Ker D, that this cocycle, this element, is in the kernel of the differential, the Čech differential. Okay, and then you have to do a little bit more. You have to check that if two torsors are here, this is about Gtorcers up to isomorphism. So you have to check that if two torsors are isomorphic, the cocycles you get differ by a co-boundary. But I'm not going to do that. You should try that as an exercise. So this claim is an exercise, and then the other exercise is that if torsors T1 are isomorphic to T2, then the cocycles you get differ by a co-boundary. Okay. So with this, we get a pretty amazing theorem. So just so I can state it in maximum generality, I'm going to tell you a proposition. So the proposition is that Čech H1. Well, this is actually true with with coefficients at any site. So this any site. And any sheaf is isomorphic to, well, first of all, it's isomorphic to locally trivial F torsors. So here F is any sheaf of abelian group, sheaf of groups, and this is isomorphic more. So locally trivial just means split by some cover, and this is isomorphic moreover. And this is if F is abelian to derived functor cohomology. So H1 tau F. Okay, so this is true. I'm not going to prove it. You can look in Milne if you want to see the proof. I'm not going to prove it because we've already claimed that for quasi-projective things, we know that Čech cohomology always computes derived functor cohomology. And this first isomorphism, the proof is more or less what we just did. So this proof is what we literally just proved. All right, are there any questions about this proposition or the previous one about Čech cohomology and torsors split by a given cover? So what we're saying, so let me just say again what this says. It says that torsors split by a given cover U are the same as Čech cohomology. Another way of saying this, or a corollary of it, is that torsors split by some cover. So locally trivial torsors are the same as Čech cohomology of X Étale with coefficients in G. And why is that? Well, it's just you take the direct limit of both sides. So maybe I'll write that down just so we know it. So corollary is that locally trivial Gtorsors up to isomorphism are canonically in bijection with Čech H1, and hence if G is abelian with derived functor H1 of the whole Étale side of X with coefficients in G. Okay, so now we can actually prove, I think, a really amazing theorem, and I think we can actually do it in the remaining 4 minutes. So Ben asks, Čech H1 always computes derived H1? That's true, and the proof is the same as usual, G of cohomology. Yeah, that's a good question, Ben. Yeah, so here's a theorem. So this is called Hilbert's theorem 90, although it's really a massive generalization of it due to Grothendieck. So you can take H1 of the Zariski side of X with coefficients in the constant sheaf GLN. This maps So Arvind asked, didn't Noether prove a more general version of Hilbert90? I don't know, maybe. So this maps to H1 of X Étale GLN, and this maps to H1, and I haven't defined this, but the definition of Čech homology in any site is the same, XFPPF with GLN coefficients. Okay, and then the theorem is that this is an equivalence of categories. Sorry, and it is a bijection. All right, can anyone tell me what the content of this theorem is? So what we've left to prove?
That Étale torsors are going to be the same as, or Zariski torsors are the same as Étale torsors, so we get a map.
Yeah, so in particular, if you're FPPF locally trivial or Étale locally trivial, then you're also Zariski locally trivial, right? Mm-hmm. So the proof is, so what you need is that torsors are the same. So like the locally split torsors are the same. And in fact, any torsor will be locally split. That's not part of the content of this theorem, but it's true in this case. Okay, and so can anyone tell me why that is? So let's just start with something on the FPPF side. So a locally split torsor on the FPPF side, and let's make out of it a locally split torsor on the Zariski side. So I claim that so the claim is that a locally split. Sorry, Ollie, I think I'm getting some feedback from your microphone.
Sorry.
GLN torsor. So I claim that this is the same is FPPF descent data, or it gives you FPPF descent data for a vector bundle. Okay, and why is that? Well, we just proved it. I mean, we just said it gives us an element of Čech H1, and that is literally descent data. Okay, and now we win, so now we're done by FPPF descent for vector bundles. Okay, so this was a little fast, so I'm going to come back and go over this in more detail next time. All right, so we're basically out of time. So let me stop here and ask if are there any questions? So Sophia asks, why is it called Hilbert90? Yeah, I think Hilbert actually did number theorems. So I think there's a couple other numbered theorems that are well known enough that people refer to them by their numbers. But I'm not 100% sure on the history, so don't. That's actually very funny. So Sophia has written theorem 0 is the Nullstellensatz, which is the zero set theorem, and if you translate it, is it actually? Do you know? Did he actually call it theorem 0? Or oh, okay, cool. All right. Well, y'all should feel free to leave. Class is over. Let me stop recording. And